Weak quantum measurements challenge our classical intuition about measurement by extracting information from a quantum system without causing a full collapse of its wave function. In conventional quantum measurement theory, measuring an observable forces the system into one of its eigenstates, yielding outcomes within a defined range. Weak measurements, however, involve coupling the measurement apparatus very gently to the system so that the disturbance is minimal. This subtlety allows the accumulation of statistical data over many repeated trials, leading to what is known as a weak value, a result that can sometimes lie outside the range of expected eigenvalues. How can a measurement yield a value beyond what we traditionally expect? Consider an example where you are weakly measuring the spin of an electron. In a standard measurement, you might obtain either +1/2 or -1/2 in appropriate units. However, using weak measurements combined with post-selection techniques, experimentalists have sometimes reported weak values that are significantly larger or even negative values that seem paradoxical when compared to the standard outcomes. This happens because the weak value represents an average over many nearly undisturbed interactions, influenced by the interference of quantum states. The paradox arises because it forces us to reconsider what we mean by measurement in a quantum context. One way to critically evaluate this phenomenon is to examine the role of post-selection. After the weak interaction, the system is later strongly measured, and only those outcomes that meet a specific criterion are kept. This selective process can amplify certain subtle features of the quantum state, effectively revealing properties that would otherwise be hidden. Could it be that these amplified weak values are not mistakes, but rather reflections of deeper quantum correlations? Many theoretical models suggest that they are genuine features of quantum mechanics, pointing to a richer structure underlying our standard measurement procedures. Another aspect to consider is the concept of uncertainty. In weak measurements, the uncertainty in each individual measurement is large, but when averaged over many trials, a precise weak value emerges. This process does not violate the uncertainty principle because the overall disturbance remains low and the statistical noise is averaged out. Researchers have used this method to probe quantum systems in ways that traditional strong measurements cannot, offering new insights into the behavior of quantum particles and the nature of quantum reality. In summary, weak measurement techniques yield outcomes that can defy standard expectations by allowing us to glimpse aspects of quantum systems that are normally obscured by measurement-induced collapse. By gently coupling to the system and using post-selection, scientists can obtain weak values that sometimes fall outside the conventional eigenvalue spectrum, challenging our understanding of quantum measurements. Could these unusual outcomes be hinting at new layers of quantum theory, or are they merely artifacts of the measurement process? Ongoing experimental and theoretical work continues to explore these questions, deepening our insight into the delicate interplay between observation and the fundamental nature of reality. In standard quantum measurement, observing a system collapses its wave function into a definite state. Weak measurement, however, allows partial extraction of information without causing full collapse, enabling multiple measurements without disturbing the system significantly. This leads to results that appear to be outside the expected range, defying classical intuition. The paradox arises because weak measurements sometimes predict values that seem impossible under standard quantum theory. For example, an experiment measuring a quantum particle's spin weakly can yield an average spin value greater than 1, even though quantum mechanics normally restricts it to +1/2. It's like peeking at a test answer without fully flipping the page. You get some information, but the final outcome remains undetermined. Quantum superposition allows a particle to exist in multiple states at once, and weak measurements probe these states without fully collapsing them. Unlike strong measurements, which force a single outcome, weak measurements reveal averaged properties of the wave function. This means that even though each individual measurement gives a standard result, the weakly measured ensemble can exhibit strange values. These results arise from interference effects between quantum paths. For example, in a weakly measured double-slit experiment, the path of a photon can be inferred without disturbing its wave-like interference pattern. It's like observing a bird's flight path through its shadows. You get hints of movement without interrupting the flight. Weak values occur when the outcome of a weak measurement lies outside the range of eigenvalues predicted by quantum mechanics. This happens because weak measurement is not directly measuring an observable, but rather the interference between different quantum states. Weak values can be larger or smaller than any expected classical measurement, leading to paradoxical results. These values do not violate quantum mechanics, but instead reflect the unusual statistical nature of weak measurement. For example, a weak measurement of momentum in a quantum system can yield a value far exceeding the maximum allowed momentum of the particle. It's like estimating the speed of a car based on a blurred photograph, where the interpretation might suggest the car is going faster than possible. Weak measurement paradoxes often arise when combined with post-selection, meaning the system is later measured in a specific final state. This filtering process enhances interference effects, making weak values appear unexpectedly large or small. Post-selection allows researchers to focus on rare measurement outcomes that reveal hidden quantum effects. This selective approach is a major reason weak measurements defy classical intuition. For example, in an optical experiment, post-selecting only certain photon polarizations can yield weak values that appear larger than expected. It's like sorting lottery winners first, then looking at ticket prices, making it seem like tickets are worth far more than their usual price. Weak measurement techniques have been applied in quantum optics to probe light polarization, phase shifts, and quantum entanglement. Since weak measurements provide information without significant disturbance, they are used to study delicate quantum systems that would otherwise collapse under traditional observation. These methods enhance precision in interferometers and quantum sensing devices. By amplifying small quantum effects, weak measurements allow researchers to detect subtle shifts in optical properties. For example, weak measurements have been used to detect tiny deflections in laser beams, achieving precision beyond classical measurement limits. It's like using a magnifying glass to detect microscopic cracks in glass, revealing defects invisible to the naked eye. The Copenhagen interpretation states that measuring a quantum system forces it into a definite state. However, weak measurements extract partial information without collapsing the wave function, suggesting a subtler form of reality. This challenges the classical view that measurement and reality are strictly linked, implying that information can exist in quantum systems in a more fluid way. Some interpretations propose that weak values represent an intermediate stage between quantum superposition and measurement collapse. For example, experiments show that weakly measured photon polarization can vary continuously rather than collapsing into discrete states. It's like listening to a conversation through a thin wall. You don't hear exact words, but you get a sense of the discussion without fully disrupting it. Weak measurement contributes to several quantum paradoxes, including the Hardy paradox, the quantum Cheshire cat, and superluminal signaling illusions. These paradoxes emerge because weak measurements reveal correlations that classical physics cannot explain. Although these results do not violate fundamental quantum laws, they expose the non-classical nature of quantum statistics. These effects push the boundaries of our understanding of reality and quantum mechanics. For example, in the Hardy paradox, weak measurements suggest that a particle and its antiparticle can interact without annihilating each other, contradicting classical expectations. It's like seeing a shadow without an object casting it, challenging common sense but not violating physical laws. Weak measurements have been used to study time symmetry in quantum mechanics, questioning whether time's arrow is as rigid as classical physics suggests. In certain cases, weak values imply that quantum systems can behave as if they were influenced by future measurements, leading to retrocausal interpretations. These observations do not allow backward causation, but indicate that quantum evolution may be less linear than previously thought. The implications suggest that quantum mechanics does not always strictly obey forward time causality. For example, experiments with quantum entangled states show correlations between weakly measured pre-selected and post-selected outcomes, implying a strange connection between past and future states. It's like reading a book where future chapters seem to influence earlier ones, defying normal storytelling logic. Weak measurement techniques are being developed for quantum metrology, precision sensing, and foundational tests of quantum mechanics. By extracting small amounts of information over multiple measurements, weak measurement allows for non-invasive probing of fragile quantum states. Potential applications include gravitational wave detection, quantum cryptography, and supersensitive atomic clocks. The continued study of weak measurement paradoxes may also provide insights into developing quantum computing architectures. For example, weak measurements have been proposed for detecting dark matter. By measuring tiny quantum fluctuations in space, it's like detecting tiny ripples in a still pond by repeatedly glancing at the surface, gathering information without disturbing the water.